Hi everyone, we are Group E and this is our project phase 2. My name is Manting Jen and my team members are Han Wang and Jian Chen. The task of our project is with a given 5.7 gigabytes of taxi fare data from New York City taxi between 2009 to 2015. And the goal of our project is to predict the fare of each ride based on the distance. So we have two data from our project. The first one is the train data and the second one is the test data. The difference between these two data is the test data doesn't have a fair amount within it because that's the goal we have to predict. And within the two data, we have the peak out time, peak out daytime, which is the time step value and the pick up and drop off longitude and latitude. And also we have the count for passenger and the fare amount. The requirement one is a visualization of the data model. The first one, we have to talk about the distribution of trip distance in kilometers. But first, we have to calculate the distance in kilometers with this formula. So you can see like the code is here and the output is here. We have the new row, the new column. That is a trip distance in kilometers. And that's a code and the output plot. So you can see like a trip distance is like the average is between like 3.8 kilometers. And then second, we have to talk about the total trips, passengers, and fare amount per year. So what is the change of total trips, passengers, distance, and fare amount among years? So here's a code to plot. And here's the output plot. So you can see like a difference between each year. And the third one is a trends in trip by hour of the day. So we have to talk about when is the peak hour and the off-peak hour of every day. So here's a code that we have to give us the output. And here's the output. So you can see the peak of hour is near 5 a.m. and the peak hour is around 7 p.m.
Okay, let's continue the feature analysis. We are going to calculate the covariance between the fare amount and the trip distance that we want to figure out their relationship. So we use that function to calculate the number of them. We printed them. This is the relationship number. Look at that. It's the positive relationship overall. Look at that. And the script data, the show distribute of horizon distance in kilometer. So yeah, we showed the table of the kilometer like it's a right skewed look like, but it's not too and we believe it's unnecessary to clean that. This table, it looks great. The next is data reduction. We are calculating new available attribute with original attribute. Therefore, the old one is no more useful. We decided to reduce them by dimensions reduction. So first, we need to import seaborne and multiple lives. It's necessary. Then we create color relationship of each feature in database. Then we put the heat map. This is what the heat map look like. Overall, we can find the pickup longitude and the drop of longitude have a low relationship in our data. So we decided to clean these two attributes as the data reduction.
Okay, so now I'm going to talk about requirement 3. So what machine learning models do we consider suitable for training? So for our project, we chose linear regression and KNN models. We chose linear regression because if there is a direct correlation between distance, which is what we will be using, and fare price, then we can easily extrapolate a prediction of fare price from the line of best fit that our model will calculate. And the reasoning behind KNN is that similar things would exist near each other. So in our case, trips at similar distances and or passenger counts would have similar fare amounts. Originally, we did not think that KNN would be very suitable for our situation because of the sheer volume of data that we have. If you recall, it's around 55 million lines. However, that turned out to not really matter because in the end, we trimmed down the data to a much more manageable size, so that we could actually process it. So now I'll be going over the code. So we started off by splitting our data into training and test sets. So our Kaggle competition did give us a training and test set. However, the test set that they gave us did not have the distance in kilometers column that our training set had. So we couldn't really use a test set. We also made that change, but we didn't. So instead we chose to just split the training set. And the training set was very large anyways, so this was fine. Right, so train test split. X was equal to our training data NYC underscore data. Everything except the fare amount column. And then Y was just the fare amount column. So here it is splitting it into the training and test sets. And this display function, it was just for me to visualize what was going on. It doesn't really need to be here. So moving on to our linear regression model. So first off, we imported the linear regression model from scikit-learn, and then we fitted it to our training set that we split earlier. And here we can see our score of 78%, which is not horrible, but not exactly amazing. And this is also how we avoided overfitting, because other than just straight up pruning any outliers, missing values, etc. in the data, another thing that we could have done was hold out data, or basically split data set into training and testing sets, which is exactly what we did here. So yeah, this entire, let me highlight this entire train test split also served the function of helping us avoid overfitting. And we can also show that our results are not an instance of overfitting by looking at these scores here. The score for KNN there, and the score for the linear regression model. So if we were overfitting our training sets, our scores would be significantly lower than what we have here. These are already not the greatest scores, but if our data, or if we were overfitting, then our scores would be significantly lower. Right? So you can see again 79. And here's our prediction. So basically it just rounds to the nearest 2 decimals. Using the predict function on our linear regression model. And DFP is just the data frame that we turn this into. So it's just easier to visualize what's going on here. So these are the actual predictions for the fare costs. So next we imported from sklearn mean squared error, which we use to calculate the RMSE. So in our Kaggle competition, the RMSE, or what was it? Root mean squared deviation was $5 to $8 on your model used. So yeah, this just calculates it, square root, mean squared error, y-test prediction, and it gives us an RMSE of 4.01. So it's below the Kaggle competitions one. And then this is just more visualization stuff to put it all into just one array, I guess. You can also find this, if you run this, it should come out with a submission.csv, and there you can see all of our, basically the entirety of this table right here. So next we have KNN, which we also again imported from sklearn, K neighbors regressor. We called it KNN, and our neighbors actually. So for this we chose 100, and this was chosen through basically trial and error to see which one gave us the best value. And yeah, 100 was what we decided on ultimately. And then yeah, this is just fitting it, and this is the score that it gives us, 79%. So it is better than the linear regression, but not by too much. And here's a prediction. Again, the RMSE, I called it RMSE2 for clarity's sake. And this one gave us an RMSE of 3.87, so again, lower than linear regression. And again, more of the same from above. This should, if you run this should give you a CSV called submission 2, which again includes all of this, because the Jupyter Notebook can't show all of it. And here we have the ensembling method. We chose bagging for this, and oh yeah. So here we have the ensembling method. We chose bagging for our situation. So right here is just the bagging for the linear regression. You can see base estimator equals linear regression, and estimator is 10. Max samples equals 1.0 because we want to use all of our data. Out of box score is true, random state 0. And then this is just fitting it. The out of box score doesn't really matter. Just did it anyways. But this score is what we really want, the score for the bagging. And yeah, if we compare the score of bagging 0.7804 to our linear regression score 0.780430, it is very, very similar, almost exactly the same, except for the last digits, of course. And then we can see we have bagging for KNN. Again, more of the same thing, fitting OOB score. And finally, the score for bagging for KNN was 0.76255. And if we compare that to our KNN score, 0.79, the bagging actually gave us a lower score than just straight up KNN by itself. So in our case, bagging did help a little bit in linear regression. However, for KNN, it actually did worse. And I just want to mention that we did look into the Google Maps API. However, given the amount of time that we were given, or rather that I specifically was given, I felt that I wouldn't have enough time to properly implement it into this project, so I decided against it. Okay, so now I'm going to talk about requirement 4, our submission. So for contributions and innovations, something that we did differently that was not present in the Kaggle solutions that we looked at was the ensemble methods that we used. So we used bagging, and bagging was not a method that was present in the other solutions. And we also used airport pickup and drop off in our project, which was also not something that the other solutions had used. As for the leaderboard, so as far as I know, the leaderboard uses RMSE, and other projects have an RMSE of about $5 to $8, whereas for our models, we had RMSE of 3.8 and 4.01 about. So our if we were to rank our model compared to other models, I think we would actually rank very high in that regard. Yeah. Okay, and here are our references. So first one, second one, and the fourth one all reference different Kaggle competitions, or Kaggle competition submissions, from which we took inspiration for our project. And the third link is just a reference to Kaggle in general.